Hi guys, welcome to the world of index laws. We're going to jump into 13D to start off this week. So just put that at the top so we know what we're working on. 13D, which is looking at solving exponential equations. So I've looked at index laws and how to manipulate them. Now we're going to look at solving exponential equations. And there's really two types of ways to do this. So the first way is to solve by making bases the same and then equating indices. Sounds complicated, pretty straightforward when you have an example here. So in this first example, we've got 3 raised to the 2x is equal to 3 raised to the 4x plus 2. Now because the bases are the same, that means if these one side is equal to the other, the indices must also be the same. So therefore, 2x has to be equal to 4x plus 2. And now I've turned it from an exponential into just a basic linear equation, which we can solve pretty simply. So all you'd have to do is get all the x's onto one side. So I'd just subtract 4x from both sides. So negative 2x is equal to 2, and then divided by negative 2, x is equal to negative 1. Okay, so the key here is to make sure the base is the same and then solve. So the first one, the base was the same to start with, so that was a one-step answer. This one here, thinking back to the skills we used, looking at 4 and 16, not the same base, so we can't equate the indices yet. But what we can do, we know we can do, is we know we can find the prime factorization of numbers that aren't in prime factors. So in this case, we'll leave the 4 to the 2x the same because we know that 16 can get down to a 4 using prime factorization, or just simple factorization. So 16, same as 4 squared, all raised to the 3x plus 1. So it's a bit different to prime factorization, is we're not going to the base. You could if you wanted to, but the idea, remember, is to get both of these sides the same. Okay, so now, simply expanding that out, 4 to the 2x is equal to 4. So remember, so that's just 2 multiplied by 3x plus 1. Remember doing a little bit of working out on the side, so that's 6x plus 2. So that's 4, so 6x plus 2. That little bit of working on the side can save you a silly mistake there, guys. So therefore 2x is equal to 6x plus 2, because now the bases are the same. So you can equate each of their indexes, okay? So negative 4x, taking away 6x from both sides, is equal to 2. X is equal to a negative half. Sorry, we ran out a bit of room there. So x is equal to a negative half, just solving basic stuff there. Alright, final example. This one looks a bit messier, but, and in this case we will go to prime factorization because we're looking to get everything down to 5. Hey, Mr. Sharp.
Hi, Mr. Collins.
So we start off with a 5n, we can't simplify that any further, so that stays the same. Multiplied by, we know that 25, factorising down primes, if you need to do the factor for you can. 25 is just 5 squared, and then it's still raised to 2n minus 1, which is that one up here, sorry it's a bit messy up there, is equal to 125, which we know, if you think about it, 5 times 5 is 25, times by 5, 125, so 5 cubed. Alright, so 5 to the n times by 5 to the 4n minus 4. Now you've got to be really careful here, guys, when you're multiplying everything in the brackets by whatever's outside here. So that's 2 times by 2n and then 2 times by negative 1. So I've realised I made a mistake there, so that should be negative 2. Okay, so that's 4n minus 2. The fact that I went back on that, do the working on the side, that stops that silly mistake, which I just made there, but I picked up on it. It's equal to 5 cubed. Now, just using index laws, bases are the same, which means when they're multiplied together, you can just add them here. So n plus 4n is 5 raised to the 5n minus 2 is equal to 5 cubed. 5n minus 2 is equal to 3. So, therefore, rearranging, 5n equals 5, n is equal to 1. Alright, we're going to keep on trucking along here, guys, because I paid, so we're going a bit over 5 minutes time, because I'm splashing out. Alright, so The second type, so if you can just get them all to every number to the same base, you can just equate indices as I've done with these three examples. Type 2 is solving using substitution and the quadratic formula, which also sounds a bit scary, but it's not too bad, okay? So here we know we can simplify this down to 9x is the same as 3 to the x all squared. It's equal to 12 times by 3 to the x minus 27. Okay, so now we've got a squared term with the same base and just the regular term here. So what we're going to do to turn this into a quadratic is let a equal 3 raised to the power of x to simplify this down, okay? So now, rather than having 3 to the x squared, we've just got a squared is equal to 12a minus 27, because we replaced 3 to the x with a for now. Looking at this, you've got a squared term and just a regular term, so let's get everything to the same side. So it's a squared minus 12a plus 27 is equal to 0. Then we think what adds to give negative 27 multiplies to give 27. So let's have a look through here. So do the multiplication first. So I know 3 times by 9 is equal to 27. But 3 plus 9 is equal to 12. But I know if I make them both negative, that's also equal to 27. Which means that this fits here. So it's a minus, remember you put your two brackets in, and you got minus 3 and then a minus 9 is equal to 0. So let's take it back up to here, guys. A is equal to 3, or a is equal to 9. And then, last step, remember we're not trying to find a, we're trying to find x. Okay? So we know that a is equal to 3 to the x. So 3 to the x is equal to 3, or 3 to the x is equal to 9. So therefore, x would be equal to, that's raised to the power of 1, or, making the same base like we did above, x is equal to 2. Alright, so key steps here is, step 1 is get the powers to have the same base, and then make a substitution to simplify, and then solve. So we'll do one more example together, and then I'll go. So this one looks a bit messier than the last one, but because we've got this extra number out the front here, which doesn't look good. But we know that whatever you do to one side, you can do to the other. So we could actually divide every term, not just each side, every single term in here by 4, and this equation will still remain in balance. Okay, so that's 2 to the x all squared, just to get that squared term out there because we know it's going to be a quadratic. Hasn't changed anything there. The 4's gone because we divided, is equal to 2 times by 2 to the x minus 1. Okay, so this is actually question 4a in exercise 3D. Okay, so we got 2 to the x squared is equal to 2 times the x. So now we let a equal 2 to the x. Okay, so now we've got a squared is equal to 2a minus 1. Now from here, it'd be great if you could pause the video, look back at your previous example and see if you can solve it. Okay, so all you'd have to do, step 1, would be get everything to the one side, minus 2a plus 1 is equal to 0. Just give myself a bit more room. Okay, and now I've got to think, once again, thinking back to our previous topics, what adds to give negative 2 and multiplies to give 1. So negative 1 times by negative 1 is equal to 1. So there'd be a minus 1 is equal to 0. Therefore a has to be equal to 1. We know that a is actually 2 to the x, so substituting back. So therefore what raised to 2 raised to what gives 1? We know that has to be 0. 2 raised to 0 is equal to 1. Okay. Thanks guys. We'll just do one more short video for the other part and then we're done.